Hey all, continuing down the rabbit hole of resources that you might not have kind of thought about at the beginning of the semester. In this section, we're going to look at a suite of minerals that formerly, they're grouped because of the process, right? And they kind of fall into a bunch of different categories. So we'll talk through them. There's really like three main ones, but we will kind of point our hat at a few others. And this group of resources, they essentially form by evaporation, meaning they're dissolved in a fluid, and as that water generally evaporates, the mineral constituent can't evaporate, right? So as water evaporates, that happens at fairly kind of low temperatures that we find on the surface of the earth, whereas the minerals dissolved in the water can't. And generally, for evaporate resources, there's really two primary types: marine and non-marine. So marine is a special term that we use in the geosciences that very specifically implies oceans and ocean basins. And non-marine, we use a word called lacustrine, which is a fancy word for lake. We're going to go ahead and start with the non-marine evaporate deposits, and I'll have to draw a couple of pictures here so you can understand what we're talking about. So here This is a lake basin. This is a type of feature that you might find really commonly in a place we call the Basin and Range, which is generally the western United States, and that's where we're going to kind of tell part of our story. And in the Basin and Range, the continental crust is being extended, as it kind of fractures, as it's being stretched. There's a series of what we call normal faults, and we get this kind of repeating pattern of mountain ranges with basins in between them. And so actually, if you stand back and look at the Basin Range province, like a physiographic map of Nevada, it's really obvious. You see these north-south trending mountains with lake basins, or what we call ephemeral lake basins, between them. And for the conditions to kind of work for our situation here, one of the most important things is that the basins essentially have no outflow. Well, how does that work, right? Every basin has outflow if it's full enough, right? If you pour water into your bathtub, eventually it's going to spill over. The same is true here. But if the other condition is met of heat, then there's actually a balance between the rate of evaporation and the rate of water that's flowing in. And in that case, the lake basin won't fill. And this can cause some really strange chemistry that we see kind of all over the western United States. Most obviously at the Great Salt Lake, right? So it's a saline lake in the middle of Utah, nowhere near the ocean. And it works exactly like this. It has no outflow. Plenty of places where water flows into it, and the only way water gets out is by evaporation, which leaves behind this kind of sludge that we call a brine. It's kind of the residual fluid and all of those minerals that were evaporated and kind of wash into there. So that's generally the story of freshwater evaporates, right, or non-marine evaporates. So when we're thinking about recovering these, there's really a couple of stages to the story. So if we go to an environment that has water, has these minerals dissolved in it, we can actually pump that water out and concentrate it in these evaporation ponds. And that's, again, something that we see all over the world. And you'll see these kind of generally brightly colored, has to do with the minerals that are in there, pools of water that are essentially more and more and more concentrated in the minerals that we're interested in. So then we can get to a situation where, if the evaporation is really won or wins most of the year, we may actually have a lake bed that most of the time isn't a lake. It might have water in it for a month or two out of the year, but other than that, it's actually just sediment. In that case, you could go in and actually mine the soil or the lake sediments that have been formed here. You may have to flush water through them and pull out those soluble minerals and then again concentrate them. So the biggest kind of contributor to what we would potentially find in one of these evaporate basins, or these kind of terminal lake basins, again using Great Salt Lake as kind of a good mental reminder, or The Alvord Desert, if you've ever been to that in Oregon, it's a playa lake bed, not too far from Boise. The Black Rock Desert, if you've ever been to Burning Man, again, is on this big playa lake, this lake bed that's only filled, occasionally with a very small amount of water. But the important thing is actually what's up here, right? So, what are the rivers flowing over before they flow into that kind of terminal lake basin? So, the rainwater that's falling kind of in the surrounding area may dissolve or somehow interact with minerals that are exposed in these rocks. That's those soluble minerals, or as those minerals undergo chemical weathering, can ultimately end up kind of creating dissolved ions in the solution of this water. Again, the water evaporates and those get concentrated. So boron is one of these minerals that's actually contained within the crystal structure of quite a few different minerals that are both in kind of sedimentary and igneous rocks. And so as that chemical weathering is occurring, boron ions will actually end up in the water and ultimately get deposited or again concentrated out of the water. You've probably heard of borax, right? So borax is generally a cleaning agent. Also, we use it to make slime if you've ever messed around. But one of the kind of industrial uses that we use is we typically mix it with silica to make what we call borosilicate glass. The trade name or a trade name of a type of borosilicate glass is actually Pyrex. So adding boron to that mixture as we're creating the glass gives it a kind of unique ability to handle changes in temperature. So cookware, lab equipment, so flasks and things like that are generally made out of borosilicate glass. Famously, there's a bunch of boron or borax deposits in Death Valley, which is another place where this would occur, right? So it's fairly low. Any water that flows in ultimately just evaporates. And there's these kind of great historical photos of, them recovering the material that they would later process into boron and hauling it out with these big mule packs, right? And actually, kind of the largest commercially available brand of borax is called 20 Mule brand, and that's actually where it gets its name. But let's move over to the next, what I think is probably the most intriguing of these freshwater evaporites. So the other one that I wanted to spend a little bit of time talking about is actually lithium. And lithium is really interesting. So it's actually used in medicine. It's used as a treatment for bipolar disorder, which again, the notion to me that there are these like naturally occurring freshwater evaporite minerals that can change the way that your brain works, I think is, again, just kind of mind-blowing. So not only does it have a medical use, but actually more and more we're starting to realize that it makes a really effective and fairly affordable way to store energy in the form of batteries. So, most modern things that you buy that have a battery, particularly if it's a heavy duty battery, like for a leaf blower or for a car, for example, we tend to see lithium ion batteries, and they can transmit energy really effectively. So when we look at the future and we look at kind of thinking about, okay, well, if we have, electric vehicles everywhere, if we really ramp up electric vehicle production, this is the primary thing that people are looking at, saying, well, okay, we're going to need this raw material to build those batteries. So the conditions that can cause lithium to form in, again, these freshwater evaporites has to do with actually, again, having the right kind of rocks here, and particularly volcanic rocks. So those with pyroxene, a couple of other kind of common igneous minerals, that contains lithium in its crystal structure, and lithium is soluble, and so as those weather, we tend to get lithium deposits. So that means if we were going to try to search for places where we would find lithium, we would want lots of volcanic activity. And in addition to that, we would also need these conditions, right? So rocks that are kind of defined by volcanic activity and intervening lake basins that dry up or are kind of terminal lakes, right? Where water flows in and just sits and ultimately just evaporates. So there's a couple of places that come to mind, at least just in the Western Hemisphere. So Chile, so South America, we've studied plate tectonics, and hopefully you guys remember that kind of along the western margin of South America is the subduction zone. We call it the Peru-Chile Trench, and that is driving volcanic activity in the Andes, right? The Andes is largely a continental volcanic arc, so lots of volcanic material, and it's also fairly dry. And so in that area, there's an incredible amount of these types of lakes. And so actually when we look at lithium resources and we look at kind of who's producing the most lithium, Chile is at the top of the list. We'll take a second after we get through this and start talking about reserves, but you'll see that some of the largest reserves do actually exist in South America. In our neck of the woods, in the western United States, well, we have volcanic activity, kind of all throughout the western United States, through Nevada and Idaho and Oregon, in the Basin Range, places where, again, this geological condition of these terminal lakes exists. So the largest U.S. deposits of lithium, and again, if you're kind of really into the stock market and kind of tracking lithium prices, because that's, a resource that will be expanding in the future, Lithium America, there's a couple of other lithium companies that are working on projects in Nevada, exactly where this is going on. And the volcanic material sourced to provide that lithium is actually the largest reserve is from the McDermott caldera complex, which, if we had kind of learned a lot about hotspot geology and maybe you'd taken a physical geology class, it's actually the oldest of the caldera forming eruptions associated with the Yellowstone hotspot. So about 17 to 19 million years ago. And the McDermott caldera complex is kind of on the Nevada-Oregon border, not too far away from Idaho, close to Jordan craters. If you've ever spent time in Leslie Gulch, right, those are all volcanic deposits associated with that. And so these lake beds in that area are being sourced with lithium from those volcanic rocks. Okay, so this is kind of a funny trumpet-looking diagram. But it actually shows lithium over time. Again, I'm not exactly sure where to stand when I have one of these diagrams going. But you can see there's really two major players. Chile and Australia kind of leading the pack. The U.S. is shown as black, so we are not necessarily a huge source of lithium, but we do have some, right? So we're going to use what we have. And again, thinking about the implications of lithium, this is really the future, right? This is the future of EVs. Are currently largely tied to lithium deposits and the use of this material. So changing our frame of view from who's producing the most lithium, we can actually take a look. This is actually from the same little infographic, but it's actually showing who is sitting on the most lithium. And surprise, South America is really running the show when it comes to this, right? So we see both Argentina and Chile up there. Australia is on there, of course. The United States, it seems like we have a lot less, and we do have a lot less, but we're still in the top 5, right? So we still have a decent amount of these resources. So it's interesting to think about the future of lithium, right? And so as we're in this kind of resource race, we can see places, particularly, again, in the United States, it's kind of what we're most familiar with, really racing to get out and produce these resources. Generally, though, thinking about how this all works, those resources are recovered by strip mining, right? So you'd actually have to go in and remove this material, and that tends to be incredibly visually disruptive. It also consumes a lot of water. So there's significant pushback. But again, I think one of the things that hopefully you've kind of learned at this point in the class is with certain technologies, you kind of have to balance. What do we find most important, right? Do we have, some environmental destruction, localized environmental destruction as a trade-off for less CO2 in the atmosphere? Or do we kind of have status quo, gasoline, conventional vehicles, and preserve some part of the Nevada desert? I don't know. It's not that straight. It's not that straightforward. Right? It's kind of a personal question, really. But one of the interesting things about mines is that we live in the modern era. There are lots of rules and regulations. It's much harder to kind of cut and run, as used to be fairly common practice, 80, actually even 40, 50 years ago. Mining companies would oftentimes leave a big mess behind. That's much harder to do now. But again, a mine can be reclaimed, right? So you can bring in, a couple of $1 million worth of soil and kind of recontour the area. That's not necessarily the most perfect solution, but it is a solution that can exist. So mining is kind of point source disruption of the land, right? And it can be a mess. It can look like it's absolutely destroyed, but it can be fixed. Whereas when we kind of earlier in the semester, we've been talking about CO2 in the atmosphere, that's a much harder problem to solve, right? We're not quite there with the technology. So, you can probably figure out which way I lean. I generally see, disruption of land as not the greatest thing, particularly if it's a place that you want to go. But we do have to kind of balance that out with the overall kind of picture of the environment, right? The overall kind of CO2 content in the atmosphere, the things that are driving warming. Okay, well now we're going to switch over to marine.